The universe is filled with mysteries. For centuries, we humans have gazed at the stars, pondered the laws of physics, and sought to unravel the secrets of the natural world. In our relentless pursuit of knowledge, we have invented tools and technologies that have transformed our understanding of the cosmos and our place within it. From the telescope to the particle accelerator, each innovation has brought us closer to unlocking the universe's deepest secrets. In the realm of artificial intelligence, a similar revolution is underway. Just as the telescope allowed us to see beyond the limits of our vision, a new technology called transformers is enabling machines to comprehend and process information in ways never before imagined. These powerful algorithms are transforming the field of machine learning, opening up new frontiers in natural language processing, computer vision, and beyond. Imagine a world where machines can understand our languages, generate creative text formats, translate languages with unparalleled accuracy, and even write different kinds of creative content. This is the promise of transformers, a technology poised to reshape our relationship with information and redefine the limits of artificial intelligence. Language is perhaps the most remarkable and complex of all human inventions. It is the foundation of our cultures, the vehicle for our thoughts and ideas, and the bridge that connects us to one another. Yet for machines, language has long been a formidable barrier, a code they struggled to crack. Traditional machine learning models such as recurrent neural networks and long short-term memory networks have made some progress in processing sequential data like language. These models excel at analyzing data in order, making them suitable for tasks such as speech recognition and time series prediction. However, they face limitations when dealing with the complexities and nuances of human language. One major challenge is that RNNs and LSTMs process information sequentially, word by word. This means they can struggle to capture long-range dependencies in sentences, where the meaning of a word may depend on another word far earlier in the text. Imagine trying to understand a complex sentence by only focusing on one word at a time. The true meaning would likely be lost. Enter transformers, a revolutionary architecture that overcomes these limitations. Unlike their predecessors, transformers process entire sequences of data simultaneously, allowing them to capture relationships between words no matter how far apart they are. This parallel processing capability is akin to how humans comprehend language, by grasping the meaning of a sentence as a whole, rather than focusing on individual words in isolation. At the heart of this breakthrough lies the concept of attention, a mechanism that allows the model to focus on the most relevant parts of the input sequence when making predictions. Imagine reading a book and highlighting the most important sentences. Attention enables transformers to do something similar, selectively attending to the most informative parts of the input data. This novel approach has led to remarkable improvements in a wide range of language-based tasks, from machine translation to text summarization. Transformers have achieved state-of-the-art results on numerous benchmarks, demonstrating their ability to process language with unprecedented accuracy and fluency. Attention is the secret sauce that makes transformers so powerful. It allows the model to weigh the importance of different words in a sentence, focusing on those that are most relevant to the task at hand. Imagine you're trying to translate the sentence "the cat sat on the mat" into French. The word cat is more important than when determining the correct French translation of sat. Attention allows the model to recognize this, giving more weight to cat when making its prediction. There are different types of attention, but the most common one used in transformers is called scaled dot product attention. This mechanism calculates a score for each word pair in the sentence. These scores represent how much attention each word should pay to every other word. The scores are then normalized and used to create a weighted sum of the input words, effectively highlighting the most important ones. The beauty of attention is that it's entirely data-driven. The model learns from the data itself which words are most important to pay attention to without relying on explicit human-defined rules. This makes transformers incredibly adaptable and capable of learning complex relationships in language that would be difficult to specify manually. Section 5. Encoding and decoding the world. Transformers typically consist of two main components, an encoder and a decoder. The encoder's job is to understand and represent the input sequence, while the decoder uses this representation to generate the output sequence. Think of it like this. The encoder reads the book and the decoder uses that information to write a summary. The encoder processes the input sequence through multiple layers, each of which applies self-attention and other transformations to create a rich representation of the input. Self-attention allows the encoder to understand the relationships between words in the input sequence, while other layers add further context and meaning. The decoder then takes this encoded representation and uses it to generate the output sequence word by word. It also uses attention mechanisms, but this time it attends to both the encoder's output and the previously generated words in the output sequence. This allows the decoder to generate coherent and grammatically correct output that accurately reflects the information in the input. Section 6. Transformers in action from text to pixels. One of the most impressive applications of transformers is in machine translation. Traditional machine translation systems often struggled with long and complex sentences, producing inaccurate or nonsensical translations. Transformers, with their ability to capture long-range dependencies and focus on the most relevant information, have dramatically improved translation quality across many language pairs. But the power of transformers extends far beyond language. Researchers have successfully applied these models to other domains, such as image recognition and generation. By treating images as sequences of pixels, transformers can learn to understand visual information and perform tasks like object detection and image captioning. For example, imagine a transformer model trained on millions of images and their corresponding captions. Given a new image, this model could generate a descriptive caption that accurately reflects the content of the image. This is just one example of how transformers are blurring the lines between different data modalities and enabling machines to process and understand information in increasingly sophisticated ways. Section 7. A revolution in language processing. The advent of transformers has sparked a revolution in natural language processing. The field of AI focused on enabling machines to understand and generate human language. Tasks that were once considered difficult or even impossible for machines, such as writing poems, composing music, and generating realistic dialogue, are now within reach. Transformers have led to the development of powerful language models like GPT-3 and BERT, which have achieved human-level performance on a wide range of NLP tasks. These models can generate human-quality text, translate languages with remarkable accuracy, and answer your questions in an informative way. The impact of these advances is already being felt in various industries. Chatbots are becoming more sophisticated and engaging, capable of holding natural and meaningful conversations with humans. Virtual assistants can understand our requests with greater accuracy and provide more helpful responses. And language translation tools are breaking down language barriers, making it easier for people to communicate and access information regardless of their native tongue. Section 8. Beyond words, transformers in other domains. While transformers have undoubtedly revolutionized NLP, their impact extends far beyond the realm of language. Researchers and engineers are exploring the potential of transformers in various other domains, including speech recognition. Transformers are improving the accuracy and efficiency of speech recognition systems, paving the way for more natural and seamless interactions with voice assistants and other speech-enabled devices. Computer vision. By treating images as sequences of pixels, transformers are achieving state-of-the-art results on tasks like image classification, object detection, and image generation. Drug discovery. Transformers are being used to analyze protein sequences and predict their properties, accelerating the development of new drugs and therapies. Genomics transformers are helping researchers understand the complexities of DNA and RNA sequences, leading to advancements in personalized medicine and disease prediction. These are just a few examples of the vast potential of transformers. Section 9. The future of machine learning, transformation and beyond. The development of transformers marks a significant leap forward in the field of artificial intelligence. These powerful algorithms are fundamentally changing how machines process and understand information, opening up new possibilities for solving complex problems and improving our lives. As with any powerful technology, there are ethical considerations that must be addressed as transformers become more sophisticated and pervasive. It's crucial to ensure that these models are developed and used responsibly, addressing potential biases and mitigating the risks of misuse. The future of machine learning is bright, and transformers are leading the charge. As we continue to explore the potential of these transformative algorithms, we can look forward to a future where machines augment our capabilities, deepen our understanding of the world, and help us solve some of humanity's greatest challenges.